Okay, so welcome to this week's class. This week's class is your last class for this module. So you should have submitted your case study earlier on today. And then this week's class is the last class. Later on in the week, your alternative assessment, which is replacing the end of semester exam. The details on that will be released to you. That'll include what you need to do, the requirements, and the due date. So this week we're going to talk about the relationship between biology and learning, and we're going to talk about a few different points of view in relation to this connection. So we're going to talk about evolutionary psychology. We're going to talk about something called biofeedback. We're going to talk about Hebb's theory, so Donald O. Hebb, who we spoke about in the biological basis of behavior module last semester. And then we're going to talk about what happens at a neurological level when we access reinforcement and what's the biological support for the concept of reinforcement. Okay, so what is evolutionary psychology? So evolutionary psychology focuses on biological and genetic accounts of human learning and behavior. So effectively, evolutionary psychology looks at classifications of human behavior and says what is the survival and adaptation advantages of these behaviors. So it hypothesizes that the human brain comprises of many functional mechanisms which are designed as a process of natural selection. So effectively saying we've evolved to the state that we are in, and our brains have adapted and evolved in a way that ensures our survival and gives us skills that are necessary for us to continue with our survival. So it talks about things like language acquisition models, incest avoidance mechanisms, cheater detection mechanisms, intelligence and sex-specific mating preferences, foraging mechanisms, alliance tracking mechanisms, etc., etc. So it says that the brain has these cognitive abilities and that these primarily are cognitive ideas. So from an evolutionary psychology point of view, it says that there are structures, physical biological structures in the brain, but that these physical biological structures give rise to these cognitive functions, which are to an evolutionary advantage for us. So, according to evolutionary psychologists, these cognitive mechanisms are designed to prolong our existence and are of benefit to the human species as a whole. So, evolutionary psychology tries to give an account of emotions and cognitions and cognitive abilities from an evolutionary point of view. So, for example, with emotions, evolutionary psychology would say that an emotion like jealousy, romantic jealousy, if you see someone else talking to your partner and you get jealous, what's the function of that? What's the evolutionary benefit of that? So, evolutionary psychology would say that that's us being protective of our romantic partners because we want to pass on our genetic material, we want to pass on our genes to the next generation. So, that romantic jealousy is because we're trying to protect our own and we're trying to protect what's dear to us. Then, in terms of cognitive abilities, our ability to acquire language is of evolutionary benefit and of survival benefit because it can help us to cooperate, it can help us with survival. So, it's important for us to cooperate and to communicate with other individuals. So, that's of evolutionary benefit. So, evolutionary psychology acknowledges these emotional and cognitive aspects of survival, and it also emphasizes the role that our genes play in terms of our behavior. So, evolutionary psychology proposes that human nature consists of obviously reactions, feelings, and thoughts, and that we all, to some extent, experience universal levels of fear, of love, and of guilt. And evolutionary psychology also says that we have an innate sense of justice, envy, and greed. And it would propose that these feelings are universally understood, and that again, they're universally understood as a species because of evolution and because of their survival value to us. But another interesting thing that evolutionary psychology proposes is that human behavior, thoughts, feelings, emotions are malleable. So they can be changed, they can be influenced, they can be adapted. So malleability allows us to adapt and survive as a species. So our thoughts, feelings, behaviors from an evolutionary point of view aren't rigid, they're not fixed, they're not the same as the cavemen. They're able to adapt, they're able to change, they're malleable. However, evolutionary psychology does make some important points, and it says that this adaptation, this malleability, isn't unending. It's not, it doesn't have all the potential in the world. It has constraints to it in terms of how malleable our thoughts, behaviors, feelings, etc. are. There are constraints to them. And so evolutionary psychology says that yes, we have flexibility in our behaviors, in our thoughts, in our feelings, etc. However, the flexibility is determined by our biology and our genetic makeup. So, for example, we might want to learn how to fly, but genetically, our body and biologically, our body can't adapt. So, no matter how many generations go by, we're not suddenly going to develop the biological ability to be able to fly. So our behaviors are malleable, they're adaptable, but they're constrained by our biological and genetic makeup. So these biological constraints can be seen in something that we call auto-shaping. So to describe auto-shaping, if, for example, we provide a pigeon with non-contingent reinforcement, so this means that they're provided with reinforcement, but not based on any specific behavior. So at random intervals, the pigeon will be provided with reinforcement. The pigeon is in a Skinner box in an operant chamber, and they're doing whatever they're doing. They're turning around, they're having a look, they're twisting, they're pecking at the screen or whatever it might be. And at random intervals, non-contingent on any specific behavior, the pigeon receives reinforcement. So this might create what we call superstitious behaviors. So the pigeon engages in behaviors that they believe created the reinforcement, even though there's actually no relationship between the behavior that they engaged in and the reinforcement being presented. This is also how superstitious behaviors appear in people. They engage in a certain behavior, something positive happens after it, and they create a superstitious behavior based on the reinforcement or what they deem to be the reinforcement of that random sporadic behavior that they engaged in. So the pigeon may learn this kind of accidental behavior, it could be twisting or swaying or whatever it might be, but there's no causal relationship between the accidental or suspicious behavior and the presentation of the reinforcer. However, what has also been seen is that if you illuminate a disc or light up a light just before presenting a pigeon with food, the pigeon doesn't have to do anything. There's no requirement of them to do anything in relation to the disc or in relation to the light. You simply light up a light in an operant chamber before the reinforcement, before the food is presented. What you find is that pigeons learn to peck at the light, even though their pecking has no causal relationship to the presentation of food. So Williams and Williams in 1969 indicated that pigeons pecked at a light even when it indicated the removal of a reinforcer. So there's no causal relationship happening here. The disc, the light, is lit up just before the presentation of the reinforcer, and the pigeons seem to be automatically pecking at this light. And this phenomenon hasn't been just seen in pigeons, it's been found in other birds. So evolutionary psychology says that pecking in a bird is a behavior that is innately, inherently associated with finding or receiving food. So evolutionary psychology terms it as a probable food-related response. So pecking effectively is automatic. It's a naturally occurring behavior. And so the pigeon pecking at the lighted disc or the light in the operant chamber relates to the pigeon's evolutionary history rather than their learned history, rather than their operant history, rather than any history that's based on reinforcement. So evolutionary psychology says that the reason that these pigeons were pecking at the light disc, even though they hadn't got any reinforcement for it, even though it wasn't the basis for reinforcement, is because of an evolutionary history as opposed to a learned history or as opposed to an operant conditioning history. Because this pecking behavior is natural, it's instinctive, and it has an evolutionary advantage to them. So it's natural for them to peck at things when it's associated with food. So at this link here, there's a video of a pigeon engaging in auto-shaping pecking behavior. So the link will be in the description box below, or obviously you can see it from the slides. So you may also want to consider that perhaps auto-shaping is under the control of classical conditioning as opposed to operant conditioning. So perhaps it's an instance whereby a stimulus evokes a response, And this response is innate, it's genetic, it's almost like a reflex response. So this stimulus presents itself or is presented, and then the pecking behavior in the bird is classically conditioned, it's associated, and it's a response. Okay, so I want to talk about this interesting phenomenon that was discovered by two of Skinner's students, and it's something called instinctive drift. So this was first identified in the early 1950s by two of Skinner's students. They were a husband and wife pair, and they were called the Brelands. So the Brelands had studied under Skinner, and they were very much inspired by this new and revolutionary science of behavior and operant conditioning and reinforcement and shaping and being able to adapt and change behaviors. So they're really excited by it, schedules of reinforcement, creating strong new behaviors. All this new science and new technology of behavior was really exciting to them. And they decided, hey, how do we get the most out of this? They trained to quite a high skill level under Skinner, and they decided to commercialize these skills. They wanted to make money from them. And the way they decided they were going to do it was they were going to train animals to perform stunts to amuse audiences. So this was 1950s America. There were a lot of traveling fairs, there were a lot of traveling circuses, and they wanted some gimmicks. They wanted something funny, something interesting, something different. So the Braylands decided that they were going to train animals to perform funny and amusing stunts and send them out to these traveling circuses and these traveling fairs. So they taught a raccoon to be able to pick up discs, to be able to pick up money and put it into a money box. They taught chickens how to pull cords to release food. They taught pigs to pick up large wooden coins and put them in a piggy bank. So they're teaching these animals a variety of different things. They're relatively human-like in their kind of presentation, and they were different from what people would have seen before. So as I said, this was in the 1950s, Midwest America, with lots of traveling fairs. And the Brelands were very, very successful in this. They trained over 6,000 animals or so, and the circuses, the fairs, really, enjoyed these animals. They said that they're great, and the Brelands became very successful. However, after a while, things started to go wrong for the Brelands and started to change with the animals. So the animals started to misbehave. They were no longer performing the tricks that they had learned, despite the reinforcement contingencies in place to provide reinforcement. So they suddenly weren't pulling the string to get the food, or they were doing it less often. They suddenly weren't, picking up the coins and putting them where they belonged. So the pigs were taking longer to bring the wooden coins to the bank, and instead they started tossing them in the air and pushing them around the ground. The raccoons took longer putting the money into the box, and they often stopped putting it in, and they kind of just dipped it in and then played with it in their hands. And the chickens stopped being able to pull the ring of the cord to release the food, and instead they just started pecking at it. So effectively what had happened was that the chickens started pecking, the pigs started rooting, and the raccoons started washing. These are behaviors which the animals naturally carry out instinctively, not due to operant conditioning. So new behaviors had been conditioned in the animals, this pulling the cord behavior, this putting the coins in the box behavior, etc., etc. These have been conditioned based on operant conditioning, based on schedules of reinforcement. But then eventually, these behaviors started to disappear a bit, and natural behaviors that the animals carried out instinctively began to drift back. So Breland and Breland 1961 said, these animals are trapped by strongly instinctive behaviors, and clearly we have here a demonstration of the prepotency of such behavior patterns over those which have been conditioned. So effectively the Breland said was that, okay, we can train new behaviors in these animals, but eventually their instinctive, natural, biological behaviors are going to overpower these new behaviors which aren't as natural or instinctive to the animals. So instinctive drift occurs when there's competition between a biologically based behavior and a learned response. So in this instance, if we take the pigeons, or if we take the chickens, for example, there were two behaviors. There was the pulling the cord behavior to get the food, and there's the pecking behavior. The pecking behavior is a biologically based behavior, and the pulling the cord behavior is the learned response behavior. So instinctive drift occurs when there's competition between these two behaviors. And what we see happening is that the biologically enhanced or the biologically based behavior is going to come to the fore. So organisms tend to revert back to the behavior that has a biological and evolutionary basis. So Breland said that this does not invalidate operant conditioning, classical conditioning, or learning principles, but emphasizes that biology has an important role and plays a critical role in the behaviors that we learn and that we're able to show. So evolutionary psychology discusses the idea of biological constraints, such as instinctive drift, such as auto-shaping. And a biological constraint can be defined as an inborn predisposition that makes certain kind of learning highly probable and easy, and other kinds of learning quite improbable and very difficult. So biologically, humans are biologically built and have a genetic ability to be able to walk. So our ability to be able to learn to walk on two legs, standing up, etc., is going to be much easier for us. If, for example, on the other hand, we were trying to be taught how to walk on all fours, not crawling, but like fully walking, so that we're bent over, walking on our hands and our feet, or if we're trying to be taught how to walk just on our hands, possibly we could be able to do it. It would take much longer, it'd be much harder. So those aren't behaviors which are biologically inherent and natural to us. Standing and walking on 2 feet is biologically natural and inherent to us, but walking on our hands or walking on all fours is not. Yes, we could probably learn how to do it. It would take much longer, be much harder, and it'd be less probable. So Breland commented, "It's very easy to condition a cat or a dog to sit still. These animals are predators, and standing still is a useful survival skill. However, it is almost impossible for a chicken to do nothing." So chickens, naturally, they don't have this sitting still, standing still ability. So training them to do that, or reinforcing them to do that, or getting them to learn how to do that is very, very difficult. Whereas with cats and dogs, that's a natural behavior to them. That's a behavior that comes easily from their biological and evolutionary point of view. So it's very easy to do that. Biological constraint favors behaviors that have survival value and discourage behaviors which put survival at risk. So, for example, chickens staying still, that puts them at risk of survival from predators. So that's a behavior that's going to be much harder to train into chickens. So other research carried out by Seligman and Hager, they commented that organisms are prepared for certain kinds of learning and what they termed contra-prepared for other kinds of learning. So again, demonstrating these prepared versus contra-prepared behaviors, these biological constraints in terms of our learning, Bowles in 1970 said that when rats are faced with danger, their natural behaviors that occur are either flee responses, fight responses, freeze responses, or frantic responses. So teaching a rat to carry out any of these behaviors in the presence of an aversive stimulus, for example, a shock, is very easy because these are behaviors that the rat naturally engages in when presented with danger or when presented with an aversive stimulus. But teaching a behavior that's the counter or the opposite of these is very difficult because, again, due to evolutionary and biological constraints and evolutionary and biological predispositions, these are the behaviors which are most likely to save the animal. So Bowles also commented that it's far easier to teach pigeons to flap their wings to avoid a shock than it is to teach them to peck to avoid a shock. So the behavior that they engage in when they're scared, when they're worried, when they're facing danger is flapping their wings, but the behavior that they engage with when they're looking for food is pecking. So although both of these are natural biological behaviors for the animal, they're context dependent and they're dependent on the situation at hand. So, for example, if you were trying to train a pigeon that in the presence of this red light, there's going to be a shock. If, when the red light comes on, you flap your wings, the shock will be avoided. That's easy to do. It's much harder to teach a pigeon in the presence of this red light, there's going to be a shock. If you peck when this red light comes on, the shock will be avoided or you won't get the shock. Because pecking isn't associated with fear, with danger avoidance, pecking isn't associated with aversive stimuli, pecking is associated with food, whereas flapping wings is associated with aversive stimuli. So it's not that it's impossible, but it's much harder. So then similarly, it's far easier to teach pigeons to peck to receive food than it is to teach them to flap their wings to receive food. So again, same premise as before, just reversed. So some psychologists say, for example, that humans have a biological preparedness to acquire language and that there's this kind of language acquisition device. So Chomsky said that we have a biological preparedness which gives rise to a cognitive function, which is called a language acquisition device. So that was one of Chomsky's arguments. And some psychologists also say that even our social behaviors are a function of inherited predispositions. I'm going to talk briefly about an area of evolutionary psychology called sociobiology. So, sociobiology is related to evolutionary psychology. It uses a lot of the evolutionary psychology principles. And sociobiology effectively says that humans are biologically predisposed to engage in certain kinds of social behaviors rather than other kinds. And this is one of their most important assumptions. So, sociobiology is the scientific study of the biological basis of social behavior. So, it believes that there are powerful underlying biological tendencies that have survived the evolutionary process, and that this process is based on natural selection and, like Darwin's theory, the survival of the fittest. But when we're talking from a sociobiology point of view, when we're talking about fitness, from a sociobiology point of view, it refers not to the likelihood that a specific individual of a species will survive, but rather the likelihood that the genetic material itself will survive. So, specifically relating to an emphasis that the quest for survival is far more important and meaningful at the group level rather than the level of the individual. So, the concept of inclusive fitness refers to the fitness of genetically related groups in terms of their likelihood of survival and in terms of procreation. So, Wilson in 1975 said that the maximum average survival and fertility of the group as a whole is the most important aspect. So, the concept of inclusive fitness is fundamentally different from the Darwinian notion of survival of the fittest individual, because inclusive fitness, from a sociobiological point of view, emphasizes that the life of a single individual is important from an evolutionary sense, but only to the extent that it increases the probability that the genetic material, the DNA, characteristics of the group will survive and will be reproduced. So, inclusive fitness differs slightly from Darwin's theory focusing on the individual, inclusive fitness saying that the value and the importance is from a group level and that it's much more important that the group survives. So, sociobiology talks about survival behaviors, and it uses examples such as honeybees, termites, and blackbirds. So, they say that, for example, honeybees and termites, they will engage in self-destructive, suicidal behaviors in order to protect their family, in order to protect their colony. So, termites, for example, are seen to they blow themselves up effectively, they explode when their colony is threatened. So if there's an intruder into their colony, they'll blow themselves up to distract the intruder and also to warn the colony. Honeybees are also seen to sting, and then they end up dying after they've stung, and they sting to try to protect their colony and try to protect their nest. So engaging in these kind of behaviors in order to protect their group, or in order to protect their family, or in order to protect their wider kind of species. And so sociobiology says that this form of altruism or self-sacrifice is present in humans too, and that it involves a sacrifice to the doer, but results in genetic advantage of the species overall. So the degree of genetic relatedness between the doer of the altruistic deed and the benefactor is of significance. So, for example, sociobiology says that you'd be much more willing to jump in front of a car to save your family member's life than you would, for example, to save the life of a stranger. So again, sociobiology kind of saying that we have these inherent genetically predisposed likelihoods and genetically predisposed behaviors, such as trying to save our family members, trying to save our friends, etc., etc. And the reason we do that is to try to preserve our genetics and try to preserve our own group and try to ensure that our family survives. So, sociobiology and evolutionary psychology both try to give an account of human behavior from a biological, genetic, and evolutionary point of view. However, neither have really gained a lot of traction, and they've both been heavily criticized for a variety of reasons, and they're still fighting a battle to stand their ground. But evolutionary psychology has taught us some interesting points, and it's important to note that evolutionary psychology doesn't try to invalidate any learning theories, doesn't try to invalidate operant conditioning or classical conditioning, but instead it draws attention to the importance of biology and the role that biology plays in terms of our behaviors. So, for example, it's much easier to reinforce and to shape certain behaviors which have a genetic, evolutionary, or biological function to them than it is to reinforce or shape other behaviors. So, we're going to talk about a really interesting application of operant conditioning, which is called biofeedback. So, biofeedback is a process which uses, as I said, operant conditioning principles. So, that being changing behavior based on the consequences of the behavior. So, is there reinforcement after the behavior? Is there punishment after the behavior? What's the schedule of reinforcement, etc., etc. So, in biofeedback, it's a procedure whereby individuals are given feedback, they're given consequences about their biological functioning. So, biological behaviors, often ones which are thought to be automatic or outside direct control, are often behaviors of interest. So, effectively, trying to see, can we control biological behaviors through operant conditioning? And the kinds of biological behaviors that we're talking about are things like heart rate, blood pressure, all these other biological behaviors which are thought to be automatic or outside of an individual's direct control. Can we influence them by reinforcement procedures, by punishment procedures, by antecedents and consequences, and the operant conditioning principles? So, what happens during biofeedback is that individuals are given feedback, and this can be good feedback or negative feedback, about these biological behaviors, such as blood pressure, brain activity, breathing rates, etc., etc. And so, this feedback acts as the consequence of the behavior. So, we have the antecedent, the behavior, and the consequence. And this feedback is the consequence to the behavior. The behavior of interest in this case is behavior like heart rate, breathing rate, blood pressure, brainwave activity, etc., etc. A lot of researchers and theorists initially thought that these kind of physiological functions, such as blood pressure, heart rate, etc., couldn't be brought under stimulus control through operant conditioning. However, research and application of biofeedback measures has indicated to us that this is wrong and that behaviors such as brainwave activity, blood pressure, heart rate, respiration rates, etc., can fall under stimulus control the same way as any other kind of behavior can. So, can we control our brainwaves? So, while you're sitting there, I just want you to emit some alpha waves. So, we spoke about what alpha waves are when we were doing our biological basis of behavior module. So, I just want you to sit there and I'd like you to emit some alpha waves for me. Can you do it? Are you doing it? Can we control our brainwaves? Well, according to biofeedback research, yes is the answer. We can control our brainwaves. We can control the kinds of brainwaves that we emit. So, some early biofeedback experiments carried out in the 1970s asked participants to control their brainwaves. So, participants were attached to an alpha recorder, and they were then asked to try to activate a specific tone as often as possible. And this tone was activated in the presence of alpha waves. So, when the participants were engaging in behaviors which produced alpha waves, this created the tone and this made the machine go off. So the experimenters used operant conditioning as an explanation, saying that the presence of the tone acted as a reinforcer to increase the alpha waves that the participants were emitting. And participants seemed to be able to control this brainwave behavior, this brainwave function, quite quickly after learning the contingency and accessing the tone. So this is an excerpt from this paper, from the Knowles 1970 paper. So 26 subjects were given baseline tests for their EEG alpha rhythms. and then a period of 15 minutes to gain insight into mental activity associated with alpha presence. So remember, alpha waves are emitted when people are quite calm, when people are quite relaxed. While they're provided with auditory feedback loop keyed to the presence of alpha. So when they engaged in activities which resulted in the emission of alpha waves, this feedback loop, this sound, this tone went off. 16 of the subjects worked with their eyes closed, and 10 with a very high alpha baseline scores worked with their eyes open. After 15 minutes practice period, permitting control of alpha through feedback, the subjects were given a trial in which they attempted to produce as much alpha as possible, and a trial in which they attempted to produce as little alpha as possible. The results indicated significant appropriate change for both the generation and suppression trials. So there was significant change on both trials when they were asked to create alpha and when they were asked not to create alpha waves. So those who were able to control alpha spontaneously reported mental states reflecting relaxation and letting go, and a pleasant effect associated with maintaining alpha. So as we said, alpha waves are kind of the relaxed waves. They're typically the brain waves that are emitted kind of just around the time before someone's going asleep. So these participants were taught kind of relaxation techniques, and these relaxation techniques resulted in the brain emitting alpha waves, and then these alpha waves resulted in activation of a tone. That tone acted as a reinforcer, and so then they were asked, okay, try to emit as much alpha waves as you can, and then this tone was presented. So this again suggests that it is possible to control physiological functions and the influence of operant conditioning on our ability to be able to learn how to control functions which we thought might have been outside of our control previously. So this is another piece of interesting research from more recent times, so from 2000. And this is using operant conditioning and biofeedback in terms of seizures. So this research was interested in looking at basic concepts and clinical findings in the treatment of seizure disorders with EEG operant conditioning. So here's just an excerpt from the paper. The first scientific paper applying EEG operant conditioning to the treatment of a clinical disorder was published in 1972, so in terms of biofeedback-based clinical disorders. This report was a case presentation involving a 23-year-old female with a 7-year history of tonic-clonic seizures of unknown origin. So tonic-clonic seizures are epileptic seizures. They're the kind of typical ones that you'd associate with epilepsy, whereby muscles kind of go into spasm and there's a lot of kind of jerky movements involved in it. So in this 23-year-old female's family, there was no history of seizures, and 2 major medical centers had failed to demonstrate a localized lesion. So they couldn't find any brain lesion to account for the seizures. So an EEG had shown a generalized 5 to 7 hertz slowing and spike wave activity that was being increased by hyperventilation. While the patient had proven refractory to numerous drug combinations, she was still being treated with a regimen of 2 separate drugs. So the drugs weren't actually doing anything for her, but she was still on them. Observed daytime seizures in the patient consisted of a wrinkling of the brow associated with a left lateral deviation of the eyes, a crossing of the right arm to the knee, and falling to the left with a loss of consciousness, tonic-clonic movements, and occasional incontinence. So that's just kind of describing effectively what her epileptic seizures looked like. The majority of incidents were nocturnal, so the majority of her epileptic seizures happened at night, occurring in the early morning hours. Carefully kept records over several years indicated a consistent pattern of at least 2 major motor seizures per month that were unrelated to the menstrual cycle. So during 3 months of twice per week EEG operant conditioning, using a light and tone rewards for the enhancement of 11 to 15 hertz waves activity detected by an analysis, the patient's seizures essentially ceased. So if you go back and if you look at the 5 to 7 hertz, so effectively what they're saying was that they hypothesized that the onset of the seizures was because of the slowing, the 5 to 7 hertz slowing and spike in the brainwave activity, or it was related to it. So effectively what they did was they used EEG operant conditioning to enhance brainwave activity to keep it at a certain level. And once they were able to keep this brainwave activity at a certain level, the patient's seizures essentially stopped. So they trained the patient how to maintain their brainwave activity level at a certain degree by using operant conditioning. So when these brainwaves were emitted at a certain level, the patient was reinforced with light and sound rewards. So quantitative analysis of the EEG over this period disclosed a significant increase in the 11 to 15 hertz band and a corresponding decrease in the slower activity. So the slower activity was the 5 to 7 hertz, and that's what they were saying potentially had a relationship with the seizures. So they wanted to reduce that and they wanted to increase the 11 to 15 hertz brainwave activity. So treatment was continued with this patient within the context of an expanded multi-subject study of this new approach, and eventually the patient became seizure-free and was withdrawn from medications and was given a driving license. So again, getting feedback, getting reinforcement, and getting a consequence of a physiological behavior such as brainwave activity. And in this case, it had quite a significant impact on the individual's life in terms of their outcomes for their seizures. So, another interesting application of biofeedback is in the area of ADHD. And there's been quite a lot of research into the use of biofeedback for improving the attention of individuals with ADHD. So, there's two articles here. The first one, which is an evaluation of neurofeedback in ADHD, and that article is going to be up on Moodle. And then the second article there, an in school neurofeedback training for students with ADHD sustained improvements from a randomized control trial. So that's an RCT looking at the effects of neurofeedback on students with ADHD. And I'm going to talk a little bit about that second study there, the Steiner 2014 study. So this is the abstract from the Steiner study. Their objective was to evaluate the improvements over the course of 6 months after 40 sessions of in-school computer training using neurofeedback or cognitive training administered to students aged 7 to 11 with ADHD. So students aged 7 to 11 with ADHD were given either cognitive training for 6 months or given neurofeedback training, which was using a computer program for 6 months. And they're interested in looking at the effects. So 104 children were randomly assigned to either a neurofeedback group, a cognitive therapy group, or a control group, and they were evaluated 6 months after the intervention. So the Conners Parent Assessment Report was used. The Conners is a very commonly used clinical psychology measure that's used to assess ADHD type behaviors. And then the behavior rating inventory, the brief, is another kind of troubling or challenging behaviors that measure that's used. And it was a double-blinded system, and they used an ANOVA as well to see if there was a difference in terms of the medication levels. They're interested in looking at whether these interventions had an effect on the need for medication. So the results were in terms of the parent responses. So the parents, typically the Conners is filled out by significant people in the child's life. So usually a teacher will fill it out, and usually a parent will fill out the Conners ADHD assessment form. So the parents had to respond with the Conners assessment form. And 6 months post-intervention, the neurofeedback participants had significant results and significant improvements on the Conners form. Then if we skip down then to children in the CT condition, so children in the cognitive therapy condition showed delayed improvement over the immediate post-intervention findings on the Conners. And then at a 6-month follow-up, neurofeedback patients maintained the same stimulant medication, so they didn't have an increase or a decrease in their medication usage, whereas participants in both the cognitive therapy and the control conditions actually needed increases in their ADHD medication. Now, not causal, we're not saying that the cognitive therapy or the control conditions caused an increase, but just appeared that naturally they needed an increase in their medication. So the conclusions from this paper then were that neurofeedback participants made a more prompt and greater improvements in their ADHD symptoms, and that these improvements were sustained over a 6-month period to a 6-month follow-up, much more significantly than the cognitive therapy participants or the cognitive therapy students or those in the control group. So this suggests then that neurofeedback has potential and is promising for attention training treatment in children with ADHD. So there's 3 videos here that show you what some of these neurofeedback programs are like for people with ADHD. One of the videos is a news report. It's an American news report. One of them is an example demonstration of the neurofeedback program in action. So you can pause the video now and have a look at these videos if you want. The links will be in the description box below, or you can get the links from the PowerPoint slides. So overall, biofeedback has been a really interesting application of operant conditioning reinforcement principles applied in a domain and an area that was previously thought not to be uh, affected by operant conditioning and learning theory. So we can see the effects of operant conditioning via biofeedback in a wide variety of areas, and it has been used for things like relieving migraines, reducing blood pressure and heart rate, and it's also been used in for asthma. It's been used, as we said, for ADHD and for seizures. So a wide variety of interesting applications of biofeedback, and biofeedback being based on operant conditioning principles. Okay, so I'm going to talk about a theory that relates learning to biology, and this is Hebb's theory. So you might remember Hebb from the biological basis of behavior module last semester. So this is just talking about him and one of his theories from a slightly different. So Hebb observed that sometimes stimulus response behaviors are immediate, but sometimes stimulus response behaviors are delayed. So a stimulus is presented and a response doesn't always immediately occur straight after the stimulus is presented. Sometimes there's a delay between when a stimulus is presented and a response occurs. And that the majority of times when it's an immediate response, it's because it's a reflex. So Hebb was interested in looking at what happens between a stimulus being presented and a response occurring in an individual or in a person. So Hebb said that something has to be happening because the response that occurs when a stimulus is presented reflects and relates to the stimulus. It's not a random response, it's not an arbitrary response. The response is caused by or related to the stimulus that's presented. So Hebb proposed that there must be higher mental processes going on in between the presentation of a stimulus and a response. So when someone is presented with something, there has to be a higher mental process that happens and then a response occurs. So Hebb described these higher mental processes as processes which themselves are independent of the immediate sensory input, but they collaborate with that input to determine which of the various possible responses will be made and when. So, for example, if you're presented with a stimulus, an auditory stimulus of someone saying hello to you, Hebb proposed that there is an internal higher mental process that isn't the same as just the sensory input. Okay, so this line that says, which themselves independent of the immediate sensory input. So it's not simply just the sound of the word hello, that there's something else going on. So the process, which is independent of the immediate sensory input, but collaborates with that input. So it's a process that collaborates with the auditory input of the word hello, and then helps you determine which of the possible responses that you have will be made and when you're going to make it. So he said there's other internal processes. It's not just a stimulus response. It's not simply that you hear the word hello and there's an immediate automatic response that you say hello back. He's proposing that you hear the word hello and then a process happens that is working with the auditory information of the word hello to determine what are you going to say back, what is your response going to be, and when are you going to give this response. So these higher mental processes are activities that influence or mediate the responses. Therefore, Hebb defined them as mediating processes. They're processes which link the stimuli and the responses to each other. So you saying hi or saying hello back or saying how are you back, that's related to and linked to the stimulus that you heard, the auditory stimulus of someone saying hello to you. But you experience it as thinking, according to Hebb. So this idea of higher mental processes and, kind of internal events, this all sounds very cognitive. So was Hebb a cognitivist? No, he wasn't. In his own words, Hebb said that the evidence which psychology can be sure of consists of what man or animal does. He also said that the evidence does not include sensations, thoughts, or feelings. Psychology is essentially concerned with such processes. They are known by inference, not directly. So effectively, he was saying that we can infer about sensations, thoughts, and feelings, but we can't directly look at them, or we can't directly, observe them, etc. So we're concerned with them, but they're known by inference. We're inferring them. We're not directly being aware of them. Everything you know about another person's thoughts or feelings is inferred from behavior. Knowledge of behavior is factual. Knowledge of mental processes is theoretical or inferential. And I think that's a really important and really valid point of view. When you're talking to someone, be it your friend, your family member, you infer what they're thinking or what they're feeling from how they're behaving. You can't observe their actual thoughts, their actual feelings, but you're inferring it from behavior, which is observable. So our understanding, in inverted commas, of internal mental processes, if we're talking about cognitive processes, is all very theoretical based, and it's all very much based on what we're inferring from behaviors. What's interesting though is where Hebb differs from other theorists. So again, this theory might not sound too dissimilar from Tolman's purposive behaviorism, but where Hebb differs from other theorists is that in his theory, those intervening variables that occur between the stimulus and the response are physiological, not cognitive. So Hebb's theory is based on neurological fact and speculation. So he's saying that the higher mental processes are physiological or biological in nature, and he's not really speculating, or he doesn't really talk much about cognition. He focuses more so on the physiological things that occur in the brain as a result of a stimulus being presented. So those intervening variables or mediating variables, he's looking at them from a physiological and neurological point of view. So Hebb argued that psychology needs to focus on and take an account of the functioning of the nervous system, and obviously particularly the brain. Now, this wasn't opposed by behaviorists. Behaviorists absolutely agreed and said, yes, the human nervous system and the human physiological system is massively important. Sure, they related a lot to reflexes, which they knew were physiological in nature. So they were very aware and weren't dismissive at all of the idea of the brain and central nervous system being massively important to behavior. But they avoided really kind of talking about it or hypothesizing about it. And primarily the reason for that was that at the time, there simply wasn't the technology and there wasn't the evidence to understand the functions of the central nervous system and of the brain. So the research just wasn't there in terms of how it directly relates to a lot of behaviors. So behaviorists acknowledged that yes, it was important and yes, it was something that had an impact on behavior, but didn't really talk too much about it because they didn't have the science or the evidence to support the interactions between biological and physiological functioning and a lot of behaviors. So there were also others who were interested in looking at the connection between biology, neurology, and behavior. So Lashley is a researcher who carried out an interesting piece of research on connections between Pavlov's classical conditioning theory and the neurological implications of such theory. So trying to examine the relationship between the neurological and biological processes that happened when classical conditioning occurred. So he set out to look for what we call the engram. And the engram effectively is a physical representation that learning had taken place. So Lashley effectively tried to find a place in the brain that represented that some form of connection had occurred. So he said, okay, if there has been this classical conditioning effect, and if there's now effectively a connection between two stimuli, that there should be a physical representation of this in the brain, that there should be a change somewhere that we can observe and that we can see. So Lashley considered that a connection between two brain areas would be a possible example of an engram. So this engram would be a physical representation that learning had occurred, and if there was a connection between two brain areas, then this would be an example of an engram, or an example that learning had occurred between two stimuli, for example. So logically, Lashley hypothesized that if learning depends on new or strengthened connections between two areas of the brain, then if we were to cut these connections, then a knife cut somewhere in the brain should interrupt that connection and abolish the learned response. So effectively, he's saying, if we're to take Pavlov's example, so if Pavlov's dogs began salivating at the sound of the bell, then there should be a connection somewhere between perhaps an auditory center in the brain and a salivation center in the brain, or something like that. So he effectively was saying that if we're learning these connections, then there should be a physical representation of this learning of connections somewhere in the brain, and this is an engram. So if we cut this connection, then it should abolish the learned response. It should abolish that salivating at the sound of the bell response that had been learned by the dogs. So, in order to search for this engram and in order to try to test his theory, Lashley trained rats on two tasks. So, he trained them on mazes and a brightness light based discrimination task, and then carried out a procedure whereby he made deep cuts in the cerebral cortices of the rats. So, again, trying to cut the connections between the areas that have been learned and that have been trained. So he found that no knife cut significantly impaired the rat's performances. And he also tested whether any specific portion of the cerebral cortex is more important than others for the area of learning. So in the trained rats, he removed large portions of the cortex. And yes, this resulted in impaired performance, but the impaired performance was based on brain damage. It wasn't based on specific areas of the brain being removed. So, in the end, Lashley proposed or hypothesized that all parts of the cortex contribute to complex behaviors such as learning, and that parts of the cortex can substitute for others. So, again, this is relatively advanced for the time. So, effectively, he's talking about plasticity, and a lot of this work would have been carried out, between the 1920s and 1950s, so over that kind of 30-year span, when the technology and understanding of things like brain plasticity wasn't very well understood, and there wasn't a lot of technology to support that idea. So we know now today that connections that are made are at a neuronal level, so they're in terms of synaptic connections, so they're much more discrete than large connections between the brain areas that Lashley would have been cutting between. So he had some interesting ideas. He, I think, unfortunately, just really didn't have the technology to examine the ideas that he was interested in looking at. Okay, so I'm going to finish this part of the lecture here, the first part. In the second part of the lecture, I'm going to talk about the biology and the biological theories of reinforcement. So, from a neurological and biological level, what happens in the brain when we come in contact with something that's reinforcing to us?